So in this video, I'm going to talk about linear regression with multiple feature vectors. And so what we're going to do is use the standard linear model package that we already did in the previous video. And then we're also going to talk about this polynomial features from sklearn preprocessing. So let me motivate this problem. So we have x in this case, where we're going to just take 20 points from -5 to 5. And we're going to assume our data, this is our synthetic data set, y is equal to 2x plus x squared plus 1 plus 2 times a normal random variable. And here we have 20 points. And so you're going to get a curve that looks kind of U-shaped with some scattering around it. And here's the plot of this. And so what we want to do is take this data from our synthetic data, and we want to fit a model y is equal to ax plus b x squared plus c to this data. And so what we're going to have to do is basically we have two sets of features that we're trying to fit first. First is our x, right? So that's a range of our x data points. And then the second one we're also going to do is x squared. So that's going to be our second feature set. So to do this, what we're going to have to do is construct a matrix where we have the first column being x and the second column being x squared. So I'm just going to do this before, kind of smaller. So maybe we have NP linspace of maybe -5 to 5, and maybe I'll take 10 data points. Oh, NumPy linspace. I always seem to misspell this. And so we already mentioned the previous one where we can take z NP new axis, and that's going to convert this array into a column vector. And so what we want to do is actually make a second column here, which will be the value z squared. So we can actually do this using this command called column stack from NumPy. And basically column stack is going to take two vectors and kind of stack the columns together. So first thing, let me just convert this to a column vector. So I have NP new axis, right? And so that's going to be, if I print x, print z, we get one column vector, and then the second column we're going to want is z squared, right? Because that's the other feature data set. So the way we can do this is just set like data is equal to NP column stack. And then we're going to do a list, and we're going to have z and z squared. And when we run this, I forgot to print this out, so we print this data, and that's going to be kind of our two columns here, right? And this is what's going to go into our linear model once we cracked it with the correct data set. And that's what's going to be used to do our model fit. So let me just come back up here. So what we're going to have is kind of our x data, right? And so me getting ahead of myself. So we're going to do model is equal to linear model. And what do I do? Underscore there. And then we're going to do linear regression. So here's our linear regression. Right? And so that's going to define our model, make sure everything's right. And then we want to do our x data, right? Because we got to get this into column form. So we're going to do NP column stack. And then we're going to do a list in here. So our first one's going to be x tilde NP new axis. And then our second one is going to be x NP new axis, again making it into a column vector. And then we're just going to square this term. All right, so that's our x data, and if we want to take a look at it, I can print x data right here, and then I have my 20 x points, and then here's just the value of those x's being squared. So this is kind of the rearranging it, kind of getting into a consistent format. Once we have this, we can do model.fit, and then we can do x data, and then y, right? And now we have our fit, right? To determine how good our model is. You know, we could also do kind of our model score. So I could print, you know, model score, x data, and y, and model. And I run it, and we see that, you know, this is the r squared value again. So this is kind of r squared is equal to %g, and then we're doing percentage. And so we're getting kind of a 95% of the variance. So the next thing we want to do is plot this up. And so we'll just do the same thing we did before. So we could do xpredict, right? So we're going to do NP linspace, and this is just to fill in the line, right? Or to fill in the curve, we're going to go -5 to 1,000. And just to make easier, I'm just going to make this directly into a column vector, new axis. And then I can do, actually I'll call this xp, and then I can do xpredict, right? Actually, I could just set it equal to itself. Let's do xpredict here, and then I'm just going to do np column stack, right? And then I'm going to have xpredict and xpredict squared, right? And then I can say ypredict is equal to model.predict xpredict, right? And everything looks good. And then we can plot up our data. So let me grab the points, right? So here are our data points. And then above this, we can do plt plot xpredict ypredict line width equal 3. Let's do color equal blue. And what did I do wrong here? I'm going to plot. I know. I plotted because this is an array. So what I want to do here is put np linspace. The reason why I'm getting kind of two curves is because this is the x1 and this is the x squared. So I'm going to do np linspace -5 to 5. Actually, I'll clean this up. Really, I should just say xp. And so this is xp, right? And then xpredict is going to be xp and xp squared. I shouldn't have rewritten it. The reason why I can't do xpredict here is because it has two columns, and so it's doing the plot of the first column and then doing the second column, and I just want this to be an array. And so once I get this together, I have my curve, and so here you see the fit of this quadratic, right? We're trying to fit ax plus bx squared plus c to our data set, and we have our curve there. And then we can do print, we can look at, the model dot coefficients, right? And our coefficients are going to be, for the first one is going to be roughly 2, and the second one is 1. And if we come up here, remember it's 2 and 1. So we're doing a pretty good job of predicting it. And then we can also print model.intercept. And we're going to have our intercept as being 2. So this would be a way of kind of fitting a quadratic polynomial to a bunch of data sets. And this is kind of fairly common in linear regression to consider not just your original x value, but also consider x squared, x cubed, and these are called features in our machine learning model. All right, so it turns out we can actually make this a lot easier. So if I do, what I can do is I can type poly is equal to, what was it called again? Polynomial features, and what I'm going to do is set 2 here, and that's going to tell me that it's a linear regression, right? I mean a quadratic, right? We want 2 polynomial features where the first polynomial feature is the linear term, and the second one is the quadratic term. And so then I'm going to do include, one other thing I'm going to do include bias, and I'll show you what happens here. So the default is include bias is equal to true, but I'm going to set it equal to false. So imagine we have some data. So I have z, and I'm going to do np linspace. And let's just do 0 to 10, and I'll do 10 points. And then I want to convert this to a column vector, right? Because that's what we're always working with here. All right. And then if I want to create kind of my data, all right, let me call this features, right? And what I'm going to do is type poly. And then the term I'm going to do is do fit transform. And then I'm going to pass in z. Polynomial features, right? And then I can print. Actually, I don't even need to define the variable. Let me just print this out. So I can print this whole term out. And then I'm going to have my feature set, right? So this is the linear term, and then this is the same thing being quadratic. If I did it up to 4th power, right? Rerun this, I'm going to have the linear, the quadratic, the cubic, and the quartic term. If I take include bias out of it, basically what it's going to do is just create kind of actually let me put this down to fewer features. So let's do 3 features. And what it's going to do is the first column here is just going to be the 0th order term. So it's going to be a constant. And this is kind of, you can think about the intercept in linear regression, right? This is just a constant term, right? So if we came back up to this model, we could think it one way to think about it is a times x, b times x squared, and then c times x to the 0th power. And sometimes you want to include that, but that's automatically included in linear regression, so we don't really need it. So that's why I do, include, what's it called? Include bias equal to false, and that just gets rid of it because it's just kind of redundant information. And this is just an easy way to construct this matrix rather than having to write all of this out. And I'll later show you when we start doing pipelines, right? And we want to test multiple models and figure out which is the best model that fits our data. This is actually going to be quite useful. So we can come back to our term, right? So we have basically our x data set. All right, so let me just redo this. We have a quadratic, right? Let me actually steal all of this up here. And I'm going to show you how you just simplify it down. So, right, so basically it's the same thing. We have our model, our linear regression, right? And so here we just do polynomial. And what's it? We're going to do fit transform on this. So let me grab this up here. I have to define polynomial. So I'm going to define the polynomial. I'm going to make it a squared term. I'm going to do fit transform x and then np new axis, and that just makes it a column vector axis, right? And so that's going to give me my x data, right? And so that's going to give me kind of a quadratic fit. And then the same way when we do the prediction, right, we're going to do the y prediction is poly fit transform xp, right? We don't have to make it a column vector because I made it a column vector up here. Basically, all we're doing is we're just using this to construct the columns where this is the linear term, the quadratic term, and the cubic term if we did a cubic term. And we could run it, and we get our same fit, right? We're going to get the same parameter values, 1.939, 1.939. All we're doing is just making it a little bit more complicated. But we could also do things like what happens if we want to fit 3 features where we have a linear, quadratic, and cubic. And so this would be like plus cx cubed, and then we could do plus d x naught. And this will actually create a model where we fit a cubic. And basically the cubic, now we have 3 parameters for the coefficients, the linear, the quadratic, the cubic. Here's the intercept, here's the r squared value. And you might see that, as we add more terms, obviously we're going to get a better model. We could also try doing like, up to x to the 5th in it. And then we can also test out this model. Obviously, as you add more parameters, you're going to get a better model. But as I'll show you later, you're going to get a bias variance trade-off with that. So hopefully this is clear. The second part is really just about automating, some construction so we don't have to do NP column stack to create the quadratic feature in our model. I'm going to stop here. If you have questions, please put them in the discussion section or post them on Piazza. Tomorrow I'll post some videos using real data sets. So we'll first use the sklearn kind of internal data sets that they use for kind of educational purposes, and then we'll grab some other data sets available online and kind of use real data sets to do at least linear regression, and then I'll talk about some other algorithms later. As I mentioned, this is not a theory class, so I'm not really going to go into theory. We're just going to really talk about, how to apply these tools to kind of fit, different kind of models to our data. All right, thank you.